Okay, hello everyone. Welcome to the SRC annual review. I'll give an overview of our task, Memory System Design for AI ML Accelerators and ML AI Techniques for Memory System Design. I'll first give an overview of the problem and background, an overview of the task very quickly, since we have done it for two previous presentations, then give an idea of the technical challenges we're solving, our goals and ideas, and mainly focus on our ideas, results, and papers from the past year. The problem we're targeting this task is computing is bottlenecked by data, and important applications like AI, ML, genomics are all bottlenecked by data, and data is increasing. These are some important applications we examine in our research. You'll see in some of the papers that are published this time. Data is a big performance and energy bottleneck in these applications, as well as other applications that are heavily employed in mobile systems. And data is key for future workloads like genomics, where data is critically increasing, and we're at a capacity where we can sequence many genomes, as COVID-19 pandemic has clearly shown us as well. And data overwhelms modern machine designs today, because today's designs are very processor-centric. They're not designed to handle large amounts of data very well. As a result, more than 60% of the total system energy spent on data moment, as we have shown in this particular paper. Our axiom in this work is that we want to design intelligent architectures. And to design intelligent architectures, we need to handle data well. This means that we need to ensure that data does not overwhelm the components and the important applications we cater for by designing intelligent algorithms, architectures, and whole system designs. We want to take advantage of vast amounts of data and metadata in the decisions that we make in the architecture. This leads us to machine learning-based systems and designs. And we want to understand and exploit different properties of different data to improve the algorithms and architectures. And today's architectures are not doing well with regards to this. They're processor-centric as opposed to data-centric. They make human-driven decisions as opposed to data-driven decisions, and they make component-aware decisions as opposed to data-aware decisions. I'm not going to go through these in detail since I've given this information in previous talks, but we want to design data-centric, data-driven, and data-aware architectures going into the future. And this task is about that, but specifically this task is about designing memory systems to handle data well. We aim to solve two different yet related problems, both focusing on ML and AI and memory system design. We want to explore memory system design for AI, ML workloads and accelerators, and AI, ML techniques for improving memory system designs. So we have two major goals, as I mentioned. We want to do in-depth exploration of memory system designs for machine learning accelerators. We want to design more efficient on-chip and off-chip memory systems. And we also want to use AI, ML techniques for improving memory system designs in particular, so that we can make machine learning-based decisions in our systems that can be much better than existing human-driven decisions. And examples are caching, memory, prefetching, and we will give examples from prefetching that's going to be published at Micro 2021. Rahul is going to talk about that in a little bit. I'm not going to go through all of these primary anticipated results and task description, task deliverables, etc. You can find this information very easily. I will introduce people. We've already introduced these people. Actually, some of them have graduated. I'll briefly mention those. These are the students who are working on the task. We will supplement with new students because some of these students have graduated. There are some senior researchers also who are working on the task. And you will see Rahul and a little bit Gagan presenting at the end of this presentation. They also have posters that you can attend. But these are our recent PhD graduates who have been working on previous years on this task, and also prior tasks, Amirali, Gagan, Damla, and Nastran. And they're either continuing at ETH or they have jobs lined up. And Sagata also kind of graduated from the program. Now he's an assistant professor at Illinois. And Minesh Patel, who is not working on this task, but who's working on an important task, is graduating from the group. So if people are hiring, certainly he would be an excellent candidate to consider. He's defending by the end of this week. So he will be looking for jobs after that. We have many industry liaisons that we interact with. And we will always welcome their feedback and others' feedback on our tasks. Okay, let me go into a little bit more detail. Clearly, I said that we have two major thrusts. We want to look at AI ML duo in terms of memory system design, how AI ML affects memory system design, and how memory system design affects AI ML workloads. And these are exploration ideas. I'm not going to go through them again. In the past, we've talked about that, but I'm going to touch the slides that I have, the progress that we have made this year have essentially touched upon all of these exploration ideas. And you can see it in the papers that I will hopefully get a chance to cover some of them, but you can also see it in the slides and the papers we've submitted. And we're happy to talk to our liaisons and other people in SRC to give more information. And these are some background works that I'm not going to talk about because we talked about them in the past. And in terms of AI/ML techniques for improving memory system designs, we also have a bunch of exploration ideas, and some of the work that we have done this year covers these 3 ideas over here, as you will see. Okay, so basically in the second part, the key idea is, can we design fundamentally intelligent architectures that are not human driven, that make far-fetched decisions, far-sighted decisions, and they basically learn from their past decisions. These are data-driven architectures where machine learns the best policies using machine learning techniques incorporated into design, into the hardware itself, so that we can actually have a much higher performing, much more efficient machine. And you'll see this in the example of Pithia prefetcher, as well as a Sibyl hybrid storage system design that I have slides for at the very end over here. And Gagan can talk about that as well. Okay, so let's go into some of the progress that we have made in this year. These were results from past year that I present in the 2020 review. I'm not going to cover them. You can take a look at the 2020 review. And these were some of the initial results, as I mentioned in the prior review, that were ongoing. Some of the ongoing works have become actually real, let's say, and they're published or they're about to be published this year. You can see in this example, this is the year 2 results. I'm going to cover some of these papers. I'm not going to be able to cover all of them in this talk. And this is the second page of year 2 results. I'm going to give you an overview of these, hopefully. Now let's go into a little bit more detail in the year 2 results. The work that Amirali has been doing on Google neural network models for edge devices has been published at PACT, and it has actually improved significantly. I'm going to give an executive summary of that. As I mentioned, we have been working on hardware prefetching designs that use reinforcement learning that outperform all prior prefetchers. I'm going to talk about that briefly, and then Rahul will talk about that for about 10 minutes after I do. We have been working on aligning refreshes with accesses so that we can improve the convolutional neural network accelerators, especially energy efficiency, by eliminating essentially read accesses or refresh accesses, depending on the way you look at it. And we see significant benefits out of that. We've been looking at synchronization support for near data processing architectures, which I will hopefully briefly talk about. And we have also been looking at end-to-end frameworks for bit serial computing using IEDM computation, which could be useful for many different machine learning tasks. Let me go to the second slide a little bit over here. We've also been looking at developing benchmark suites for processing in memory, which includes a bunch of machine learning workloads as well. And we have a methodology for deciding which tasks or which parts of a workload should be offloaded to a near data processing engine, or which part should stay in the processor. And we have a paper related to that that's recently published. I'm going to briefly talk about that, hopefully. And we have also been doing studies on real processing in memory architectures, the UpMem processing in memory architectures, and we have a detailed results related to that. I'm going to briefly talk about that. We've also been looking at FPGA-based near memory acceleration methods of real applications like genome analysis, weather prediction, and also machine learning. And we have a paper related to that as well. And we have also written overview papers on processing in memory in the past year. As I mentioned, we also look at the applications, the use of reinforcement learning for improving other aspects of the system, like data placement in hybrid storage systems. And I have slides related to that, but probably I will not have a chance to talk about that. Now let's talk about some of these works, some of these recent results in 2021. Since the last review, let's say. This is, as I mentioned, Amirali's work that was published in PAC 2021. Basically in this work, we analyzed a state-of-the-art edge machine learning accelerator, Google Edge TPU, using 24 proprietary Google Edge models, which includes convolutional neural networks, RCNNs, LSTMs, and transducers. And these exhibit very different properties according to our analysis. And we find out that a monolithic accelerator suffers from 3 challenges. Basically, it's not very efficient in terms of peak throughput. It's not very efficient in terms of energy efficiency, and it's not very efficient in terms of memory system. And the main culprit for this is that there's a single accelerator that's trying to cater for all kinds of layers from all kinds of different models. And basically, the answer, the solution that we have is to have a heterogeneous accelerator that's designed for different types of layers, let's say clusters of layers. And we map these have different data flows and different specializations. For example, we have 2 data-centric accelerators versus 1 compute-centric accelerator in Mensa. And then we have a runtime system that maps the incoming layers to the different accelerators and orchestrates data movement between them. And if you actually design such an accelerator, we have a version of this with 3 different accelerators for Google Edge machine learning models. And we find out that Mensa improves performance and energy efficiency by 3x and 3.1x for these models. And it also reduces cost and improves energy efficiency compared to monolithic accelerator, which has to be designed to cater for kind of the worst case, if you will. And I'm not going to go into the details of this. We have a paper related to this, which is already uploaded on the SRC website. It's also an archive. But basically, as I mentioned, there's significant variation in terms of layer characteristics across the models. There's significant variation in terms of layer characteristics within a model as well. And a monolithic accelerator, unfortunately, is very inefficient in many aspects. And Mensa essentially does this. It takes a monolithic accelerator. It really designs accelerators for clusters of layers. And we have a runtime schedulers that I'm not going to talk about. Unfortunately, we don't have time, but you can read the paper for more details. Okay, let me quickly introduce Pithia. Pithia is a customizable hardware prefetching framework using online reinforcement learning. Basically, the idea is to use reinforcement learning in the design of the prefetcher such that the prefetcher can learn using multiple program features. It can be system aware. It can take into account memory bandwidth utilization, for example. It can be customizable for different rewards and different long-term objectives, let's say. And reinforcement learning enables this in a nice way, because once you formulate something with a reinforcement learning, you have state, action, and rewards. And you can actually take into account different states, make different actions based on some algorithms, reinforcement learning algorithms. It can also change the reward function, either dynamically or statically. And we demonstrate this in the Pithia paper, which Rahul is going to talk about more. And we see significant performance benefits over the state-of-the-art prefetchers. And this is also completely open sourced and artifact evaluated. Again, I'm not going to talk about this in detail because Rahul is going to talk more about this, as I mentioned. Okay, I'm just going to go through the slides basically that hopefully will give you an overview, and Rahul will take over. Basically, the takeaway is that reinforcement learning in a prefetcher gives you significant performance benefits the way we design Pithia. Okay, next, I'm not going to talk about the refresh triggered computation. You can find the slides for it and also the paper. Synchron, as I mentioned, this provides efficient synchronization support for near data processing architectures. This synchronization is very important for large-scale machine learning applications, especially. And this is the first end-to-end synchronization solution for near data processing. And we see significant performance benefits over past solutions that are applied to near data processing, let's say. And it's very close to a zero overhead synchronization scheme. And we have a classification of different synchronization solution spaces, as you can see, and we make some design choices, as you can see in these slides, but I'm not going to go over these. You can read the paper for more detail. Finally, along these lines, we have near data processing, and we have an near data processing framework, SIMDRAM, that can do processing using DRAM operations like bitwise majority, bitwise not functions. And essentially, this is an end-to-end processing using DRAM framework that provides a programming interface, ISA, and hardware support for efficiently completing complex operations in DRAM, providing the ability to implement arbitrary operations as required, and using an in DRAM massively parallel SIMD substrate that requires minimal changes to DRAM architecture. This is based on the Ambit work that we have presented in the past SRC incarnations, if you will. And we see significant benefits on many different applications as well, including some machine learning applications. Again, I don't have time to go over it, but you can read the paper or contact us if you have any questions. Okay, I'm going to go through this relatively quickly because we really do not have much time. I don't want to leave enough time for Rahul. But just to give you an idea of the key results of SIMDRAM, we see significant performance benefits as well as energy efficiency benefits over CPU and high-end GPU in 16 complex DRAM operations and 7 real-world kernels. Okay. Let me give you a quick overview of some of the other works related to near data processing. DAMU is one example where here we develop a methodology to identify source of data movement bottlenecks, and we compare compute and memory-centric data movement mitigation techniques. And we also have an experimental characterization of more than 77,000 functions across 345 different applications, and a methodology to characterize these applications based on data movement bottlenecks. And we release a benchmark suite with 144 very selected functions, and we have a bunch of case studies. I would recommend you take a look at that, but essentially we're motivated by near data processing engines that look like this, and near data processing has been shown to be very powerful for many different applications. But the question is, of course, how do we decide what to offload near data? And we develop a methodology for that essentially in the DAMU work. And we analyze a bunch of applications, as you can see in this slide. And you can characterize different memory bottlenecks. And depending on that, we provide solutions as to how they should be handled. And this is all open source. Again, you can find it online. Feel free to give us any feedback. Okay, I'm almost done. I will mention we have a modern primer on processing in memory that we have recently written that covers a lot of issues related to processing in memory, including issues related to machine learning, etc. And we are happy to get feedback to improve that. And finally, we have some work that analyzes the UpMem processing in DRAM engine very, very rigorously. You can see this is real. This is a real near data processing system where you have processors inside a DRAM bank. And Juan has done a lot of work related to this. He has also a bunch of talks related to this. I'm not going to go through the details of this since there's a lot over here, but basically we provide programming recommendations as well as takeaways related to UpMem architecture. And these are some of the key takeaways, basically. The most suitable workloads are memory bound, clearly. And you can see that there are some cases workloads are much better than existing GPUs. And these workloads that are well suited for the UpMem architecture usually use simple or no arithmetic operations, as you can see. But we also analyze the downsides of the UpMem architecture. This is all open source. Again, you can find prim benchmarks online. We have released benchmarks as well. Okay, this is, I think, where I will stop. You can feel free to look at the other slides. And I will hand it over to Rahul so that he can talk about the Pithia work. Thank you very much. And I'm happy to take questions after Rahul presents.